In machine learning, getting a perfect score, well, it's not always a good thing. Actually, it can be a massive red flag. It can signal that your model is an absolute genius in the classroom, but completely useless out in the real world. Today, we're going to dig into this really weird paradox, the problem of overfitting, where a model can literally know too much for its own good. Let's get into it. So, picture this. You've spent weeks building a model. You train it on your data, and boom, it gets a 99% accuracy. You're thinking, I've done it, I've created a genius. But then you give it some brand new data it's never seen before, the final exam, and it just completely bombs. We're talking a score that's barely better than just guessing. This exact scenario, it's one of the single biggest hurdles in all of machine learning. To make this super intuitive, let's think about two kinds of students. Over on the left, you've got the memorizer. This is the student who crams like crazy, memorizing every single question and answer from the homework. They'll ace that homework for sure, but the second they see a question on the final exam that tests the actual concept in a new way, they're totally lost. Now, on the right, you have the learner. This student is all about understanding the underlying principles. They might not get a perfect 100 on the homework, but because they get it, they can apply that knowledge to solve new problems on the final. When we build models, we are always trying to build the learner, not the memorizer. Okay, so this whole idea brings us to what's called the fitting spectrum. See, when a model learns from data, its performance can fall into one of three main categories. And our job is to find that perfect balance, that just right Goldilocks. So on one end of the spectrum, we have what's called underfitting. This is when the model is just way too simple. It can't even capture the basic patterns in the data. This is like our student who just skimmed the chapter headlines in the textbook. They haven't learned enough to do well on the homework or the exam. The model's just bad everywhere. And on the complete opposite end, we have the problem we started this whole thing with, overfitting. This happens when the model is so ridiculously complex that it doesn't just learn the pattern, it starts memorizing the training data itself, including all the random little quirks and noise. This is our memorizer student. It does brilliantly on the stuff it's already seen, but it completely falls apart when it sees anything new. And then, right there in the middle, that's the magic. That's the sweet spot. We call this a good fit, or generalization. This model is smart enough to capture the real underlying pattern in the data, but it's also simple enough that it knows to ignore the random noise. It does well on the training data, and this is the crucial part, it also does well on new, unseen data. This is what we're always aiming for. So let's put a formal definition on it. Overfitting is a modeling error that happens when your model gets way too cozy with the training data. It learns it so perfectly that it even starts learning the noise and the random fluctuations. And because of that, it fails. It can't make good predictions on any new data. It's basically memorized the past instead of learning how to predict the future. Now, how do you actually spot this in the wild? Well, it's pretty straightforward. You just compare your model's performance on the data you trained it on with its performance on new data it's never seen before. If you see a massive gap, like a 99% accuracy on the training set, but it drops to 55% on the test set, that is a classic textbook sign of overfitting. Your model aced the homework, but it's failing the final exam. So the big question is, why? Why does this even happen? Well, the reason is rooted in a really fundamental concept in machine learning, this constant tug of war we call the bias-variance trade-off. All right, let's break this down. Bias is basically the simplifying assumptions a model makes. A model with high bias, that's the one on the left, is too simple. It's like trying to draw a straight line through a bunch of points that clearly form a curve. It's just never going to capture the real relationship. That leads to underfitting. On the flip side, you've got variance. This is all about how sensitive your model is to the training data. A model with high variance, like the one on the right, is way too complex. It draws this crazy squiggly line that hits every single data point perfectly, but that line is absolutely terrible for predicting any new points. And that, right there, is overfitting. So you see the problem, right? It's a constant balancing act. If we try to make our model simpler to lower its variance, we usually increase its bias. And if we make it more complex to lower the bias, we risk jacking up the variance. The name of the game is to find that perfect sweet spot, a model with low bias and low variance. That's how we get that good, generalizable fit. Now, the great news is that we're not just helpless here. Data scientists have a whole toolkit full of techniques designed specifically to fight overfitting. These are tools that help guide our models to actually learn instead of just memorizing.
So let's pop open that toolkit and see what's inside. Here are some of the heavy hitters. Simply training with more data can often help a lot. There's also feature selection, where you simplify the model by getting rid of irrelevant inputs, and things like pruning for decision trees, which is like trimming off dead branches. But let's zoom in on two of the most powerful and common techniques out there: regularization and cross-validation. Regularization is a really clever idea. The way it works is it adds a penalty to the model for being too complex. It's basically telling the model, hey, I want you to fit the data well, but I'm going to punish you if your parameters get too extreme or crazy. This is what stops the model from drawing those wild, squiggly, overfitted lines we saw earlier. Now, you'll usually hear about two main types, L1 and L2. L2, which is also called ridge, gently pushes the model's parameters towards 0. It makes the model simpler, but it keeps all the features in the game. L1, also known as lasso, is a bit more aggressive. It can actually shrink the parameters of less important features all the way down to exactly 0, which means it's effectively kicking them out of the model entirely. So it does feature selection for you automatically. Pretty cool, right? Okay, next up, we have an incredibly powerful technique called cross-validation. Remember how we can spot overfitting by comparing the training and testing scores? Well, cross-validation is a much more sophisticated and reliable way of doing that. It lets us get a really solid estimate of how our model will perform on unseen data, all without touching our final, precious test set until the very, very end.
So here's how a popular method called k-fold cross-validation works. First, you take your training data and you split it into, let's say, 5 equal chunks or folds. Then you train your model on 4 of those folds and you test it on the one you left out. Then you do it again, training on a different set of 4 and testing on a different one. You repeat this whole process 5 times, making sure each fold gets a turn to be the test set. Finally, you just average the performance scores from all 5 of those runs. What you get is a much more stable, much more reliable estimate of how your model is actually going to do in the real world. So, after all this talk about overfitting, bias, variance, penalties, and toolkits, what's the actual point? What is the ultimate objective here? Well, it all comes back to one single, crucial concept. The true goal is generalization. It's the model's ability to take what it's learned and apply it correctly to new data that it has never, ever seen before. It really is the difference between just memorizing a bunch of facts and actually gaining a true understanding. A model that generalizes well is a model that is actually useful. And that really just says it all, doesn't it? We're not trying to build models that are perfect students of the past. We're trying to build models that are wise predictors of the future. The goal isn't a model that knows all the answers from the textbook. It's a model that understands the questions it has never seen before.